Yeah. Hello, everybody, and welcome to our webinar on 5 ways to make your ClickHouse slow and how to avoid those ways. My name is Robert Hodges. I'm going to be here today with Mikhail Filimonov, and we are going to get started in 1 minute because I'm going to give people 60 seconds to join. We had a bunch of signups. Hopefully, more people will be dropping in, and then we'll get started. So I'm going to mute, and we'll be back in 60 seconds. Thank you very much. All right, the 60 seconds are over. Let's get going on 5 ways to make your ClickHouse slow and how to avoid them. My name is Robert Hodges. I'm CEO of Altinity. I have with me here today my colleague Mikhail Filimonov, who's our ClickHouse architect, and we are going to be talking about ClickHouse performance. Before we dive into this, I'd like to just cover a few brief things that will make this webinar more fun and enjoyable. First of all, it is being recorded. Not only that, we will give you that recording as well as a copy of the slides. So no need to make hasty notes. You're going to get it all in email within a few hours of this talk ending. Another thing, we have time for questions. And in fact, Mikhail is here and can help answer questions both in foreground as well as in the background. If you do have a question as we're going along, please go ahead and just pop it into the Q&A box. It's available on the Zoom, the little Zoom menu bar. And there's also a Q&A. We don't stand on ceremony here. Excuse me. There's a chat. You can throw questions in there as well. We will answer them no matter where you put them. And we should have a little bit of time in the end to answer extra questions. And so don't hesitate. If there's something you want to know, just throw it out there and we'll answer it if we can. With that, let's get going. So, quick introduction to Altinity. If you haven't heard of us, I know that many of you are friends and have been working with us for years, or like or otherwise contribute to the ClickHouse community. So we are a vendor for ClickHouse. We are not the same as ClickHouse Incorporated. We're in fact we collaborate on open source, but in fact we are uh, competitors in the market. What do we do? Well, we started out offering enterprise support, so 24/7 support for ClickHouse for any purpose, everything from embedded systems to huge cloud clusters with hundreds of nodes. We also run Altinity.cloud, which was the first cloud for ClickHouse introduced in North America on Amazon and has been going strong for 6 years. We also, if you've been around, you may be aware that we are the authors of the Altinity Operator, very, very popular way of running ClickHouse on Kubernetes. And we also have something called Project Antalya, where we're adapting ClickHouse to work to use Iceberg as native storage. Those are all things we work on. We'd be happy to talk about them. You can ask questions, check with us later. But today we're going to talk about performance. So let's dive in and learn about it. Excuse me. So to get started, what I'd like to do is just give a quick overview of the ClickHouse architecture. I think most people on the call are pretty familiar with this, but let's just review it in case you're not. So ClickHouse is what we call a real-time analytic database. It's designed to read large quantities of data very, very quickly, also to ingest them quickly and to give answers to across potentially data sets that extend into trillions of rows. Um, the architecture that ClickHouse is based on is what's called shared nothing. This is a traditional architecture, particularly for analytic systems. It's been around for decades at this point. And the way that it works is you have ClickHouse servers with attached storage. So block storage, for example, if you're running Amazon, that would be EBS. In another cloud, choose your favorite storage. It could be attached NVMe SSD if you're running on your own rack machines. And those servers are then connected across a network. And when we make tables, we can have them be replicated so that you can basically give updates to any of the tables, and the replica, the parts that are loaded into one replica will automatically replicate to others. The way that that works is that we have something called ClickHouse Keeper. Used to be Zookeeper. It's now shifting to Keeper, which is a rewrite of Apache Zookeeper in C++. That maintains a list of who has which parts so that ClickHouse knows how to move the data around so everybody has their own copy. We can use block storage, as I mentioned. Over time, ClickHouse has become very, very good at also reading data from object storage, particularly S3 object storage, but also the native APIs of Azure and Google. And that's something that we've talked about in other webinars. We won't be touching on it too much here. So this is the basic architecture. It has grown over the years, and it's become extremely popular. So what do people do with it? Well, the canonical system that you build with ClickHouse is what we call a real-time event pipeline. Imagine, for example, that you have a security management system, which is reading things like DNS requests. Those could be collected from different sources, excuse me, from individual machines that are making DNS requests. They could be fed into an event stream like Kafka to sort of buffer them up and separate the producers of this information from the consumers. Kafka would deliver it to ClickHouse, which uses, and then it would be put in merge tree tables. Merge tree is the workhorse engine for large big data, and this would be in a ClickHouse cluster, just like what I showed you. And it would, this data, which can arrive very, very rapidly, often millions of rows per second, is used then to feed various things that are useful to users. So this is a security management system. You could have real-time dashboards that detect and show interesting things. For example, rules violations that you should investigate. It could be used to supply APIs that are used to feed applications that do interesting things like assess security posture. It could also be used to generate alerts. These are standard things that people build on the application side, but the core storage engine is ClickHouse itself. So this has become very popular. Question is why? And so it's worth looking at a small example. This is, and in fact, in this talk, I'll mostly be using examples drawn from a very popular data set called OnTime. This is a sample query, which is designed to, this OnTime data set has a row in it for every commercial flight in the United States for the last 30 or 40 years. We have a subset of it, but it has about 200 million rows in it. And this is a query that's asking to show the carriers that have the worst performance for cancellations. So there's a carrier here called G4. I actually don't know which airline it is, but this is not one you want to fly on. They had 16% of their flights canceled in 2020. Now, notice that this is you can see the performance numbers below. This scanned just under 200 million rows to get this result. It came back in less than a second. Now, you might think that that isn't super fast, but if we go to the next slide, we did everything possible to make it slow. So we're using an Oz M7G X large graviton that has four vCPUs. There's actually 16 gigs of memory available. We only allocate 14 in this using C groups in this particular exercise. We also use very, very slow storage. So we've set the EB, this is running the cloud. It's using storage set to 125 megabytes per second. This is really slow. This is like the old SATA desk drives. And we've got a special setting when we run the query, which is forcing it to do cold reads, to use direct IO, skip the buffer cache. And yet we still get results under a second. If we tune these up, have bigger instances, allow the query to use data that's resident in RAM, it becomes much faster. How does it do this? Well, the secret is columnar storage, and columnar storage is compressed, and as a bonus, that we access in parallel. So to just be totally clear what's going on here, if you use a database like Postgres or MySQL, these databases store the table data in rows. So in this particular table, we have 109 columns. If you touch any of the values of any of the columns for a row, you will read the entire row on MySQL or Postgres. And another side effect of that is the rows tend to be minimally compressed or not at all. In fact, in MySQL for many years, it had compression, but most people left it turned off because it was kind of a performance drag. ClickHouse, by contrast, stores the data in rows, or excuse me, in columns. So you have 109 columns, and each of them is actually stored in two files. Uh, there's a file with a bunch of offsets, and then there's the actual data. So excuse me. So what that means is if you have a query that touches three columns, like the one we just showed, you will only read the files that have that column data. This is very, very efficient if you want to scan wide tables and particularly do things that involve full table scans like that query. So ClickHouse is very good at this, and this is a picture that kind of illustrates why the math on this is so good. So imagine what I'm showing here is these circles, and imagine that these are spheres that represent the volume of data we're reading. So in a row database like MySQL, that query would have touched every row, and uh, and as a result, it would have read 61 gigs of data. And on MySQL, that would be single threaded. So that's a lot of data, a single thread. This would go away for a while. In ClickHouse, because it's columnar, we have columnar storage, it's going to read three columns. And so right there, we're going to cut down the data by 98.5%. So we're only going to read about a gig of data. Um, uh, when it's expanded in memory, but actually the data read from disk is only 17 megs because it turns out the data that we're accessing compresses extremely well. And so this is a reduction in data of 3 to 4,000x, which is a thing that makes it possible for us to do a full table scan efficiently. Finally, ClickHouse is very good at parallelizing. In this particular case, actually in this, it's not 8 threads, it's actually 4 threads. So each of these would read 4 MB of data. This is why ClickHouse is fast, particularly when it's combined with optimized hardware and a lot of memory. Uh, it rips. So with that, it just seems like life is good and we don't even need to talk about performance. Well, it turns out it's not quite that simple. So let's dive in and find out what are some of the things that could actually go wrong and that you're going to have to deal with to get the performance that ClickHouse is so famous for. So the first problem that people tend to run into, and the one that when we work with ClickHouse users or are designing systems ourselves, is tables design. This is the first place that people land, and particularly if you haven't used ClickHouse before, this is something that's really important to understand how it works. Let's have a look. So ClickHouse, like many analytic databases, breaks up tables into pieces. These are called parts. And so there's when you have a ClickHouse table definition, and this is a short form of the leaving out the columns, but it shows the basic table definition. So create table, it's called default.onTimeRef. The engine is merge tree. So this is our workhorse engine that's going to give access to the data. And it's going to include two really important clauses, a partition by clause. And what that says is take the table and break it up into pieces or into sections, if you will. And those sections are divided by year. The second thing it has is ordering. So within those sections, we're going to have we call them partitions. We're going to have parts, one or more, and those parts will be ordered by the carrier, that is to say the airline, followed by the flight date, the date that the flight took place. And so if you go into go onto the host where this is running and you look on disk, you will see a bunch of parts, for example, with names like the following 2017, that's the date, and then some numbers that follow after it that show how many times these parts have been merged. So that, and this is something that ClickHouse does in the background, and we'll talk about in a second. But basically, the table is broken up into pieces. And excuse me, ClickHouse asks you, one of the conditions of using ClickHouse is that ClickHouse wants you to make this decision for it to tell it what the best way to partition the data is. It doesn't do it automatically. And as a rule of thumb, you want to get about 1,000 parts or so. You can have more, you can have less, and it'll work fine. But if you have a lot more, it won't work well. We'll see that in a minute. The second thing is the sorting. So this just shows the layout within a single part. We have something that's called the sparse index. It's basically like a primary, we call it sometimes call it the primary key index. It is designed to fit in memory, which means it doesn't store entries for every single row, but by default for about every 8,000 rows or so. And then what that does is if you can use these values, they then point to offsets in the files that represent the different columns. Remember I said that there's two files. One's the offsets, and then there are things called granules, which contain the actual data. So these are highly compressed, and you can also have indexes on them. So that's how you lay the storage out. You have to make this decision for yourself. There's rules of thumb here about how to do it, but this also gives you the opportunity to make mistakes. And this is a big place where people get in trouble, and that then leads to poor performance. Let's make a change to this. And what we're going to do is partition this by the carrier and also break the parts up by month. It's a pretty reasonable, it seems on the face of it, a pretty reasonable thing to do. If you've worked in multi-tenant systems, for example, if you worked with MySQL, it's very common to put each tenant in their own database. So why not put each tenant in their own parts? Because then, for example, if we get a GDPR request, we can just drop all the parts from that tenant and they're out of there. So this is a very reasonable thing to do, but it actually has some kind of bad effects on performance. So so we're going to create the table that looks like this, with this partition by, and we're going to take the data from our test table, on time ref, and we're going to go ahead and insert it into this. And by the way, this is a nice trick for how to do this on small tables. You'll see I have these settings: max threads equal 1, max insert threads equal 1. ClickHouse is very resource hungry. And by default, it will try to use all the vCPUs available to it. In other words, all the hardware threads. If you let it go, it can run out of memory sometimes because those will consume too much memory. So that's why we have these extra settings. What happens when we do this? Well, if we run that same query again, it becomes vastly slower. So remember, it was less than a second. We have highly unoptimized hardware, but at this point, that query has gone to 5 seconds. So it's increased by something like 6 times over the original performance. And that's simply because by making this choice, we've increased the number of parts, and each of those parts has files for 109 columns. We have a vast number of files that ClickHouse now needs to open up and look at to do this scan. So in fact, we can see the differences here, that when we partition by year, we get very good performance. The blue stuff is the cold run when the disk caches are not, or the memory caches are not full. It gets much faster, or gets quite a bit faster as once we have RAM. And then of course, when we do a cold run, reading directly from storage is very expensive because we just have to open up and read a lot of files. So this is bad. So the question is, why was it so bad? Well, it turns out that if you are in analytic systems, it's often a really, really good idea to just partition by time. And the reason for that is if you look at airline flights, about the same number of flights happen every year. So that means that we get partitions that have about the same number of flights per unit time. And so they tend to have even sizes, and they tend to be pretty large. It turns out there's about something like 5 million flights a year that go into this database. And you can see that with these dots on the left. If we split things up by carrier, there's a huge amount of variation between the size of carriers. So Southwest does the most flights in the United States of any airline. Actually, that's not entirely true, but excuse me, it is the absolute number of flights. It's about 1/7 of the commercial flights in the United States. So there's a huge, huge variation in the number of flights per carrier. And what that means is at the tail, you get a huge number of very small parts. These are bad. So because they're slower to open up and read. So that's something you want to avoid. And that's why we generally say that if you want to avoid performance problems, you want to follow this cheat sheet, which is that when you partition a table, you do it by time, and you pick some reasonable period of time. If you're holding data for 14 days, partition by day. If you're holding it for weeks, by weeks. In this case, we have 30 years of data. Partition it by years. The second thing, and this is something that you have to fight against if you're used to other databases, you don't split the data for the tenants. You sort it. So what that does is it arranges your tenants into contiguous sections of data. So the queries are really fast. It's all located on the same part of storage. What that does mean, the trade-off is that if you do need to remove a tenant, you'll actually have to update the parts. But generally speaking, in many of these systems like observability, that's a small price to pay, especially if you don't keep the data for too long. And so this is a really good way to do it. There are other things that you can do for performance of schemas, like using the proper data types, using what are called codecs. These are things which change the data, morph the data before it's handed over to compression. And then finally, if that's still not enough, you can switch from the default compression, which is LZ4, to ZSTD. This is something we only recommend. ZSTD is actually pretty efficient and it doesn't use a lot of CPU. So we only recommend doing this when uh, uh, when you've actually got idle CPU capacity, but you're seeing that your I/O is taking up too much time. And Misha, I don't know if you're watching this, but there's a totally relevant question that just popped up. How does partition by affect background merges? That is to say, with no partition versus partition by date. Yeah, for large systems, you definitely want to have you definitely want to have a good partitioning scheme that results in nice large partitions. If you Because there's another thing that can happen if you don't get the partition by right, it can cause undue merging as new data arrives because the if the parts are small, ClickHouse will say, "Hey, I want to make them bigger," and it will just as new rows arrive, it will tend to go back to the small, to your small partitions and try to make them bigger, which will lead to more merge activity. In fact, I know Misha is putting in an answer for that, but in fact, that's a really great segue into the next performance problem that you get with ClickHouse. Oh, before I get to that, measuring compression. One of the things I love about ClickHouse is it has the best system tables of any database I've ever worked with. They are really, really powerful and easy to read. One of the things that they do is they allow you to measure compression levels in a variety of different ways at the part level, at the table level, at the level of columns. This is a typical a query that you would run to find out what's the compression for those columns that I was reading in that sample query, carrier, flight date, and canceled. And this will just burp it out, and this format readable size makes it human readable as opposed to like a long number that gives you the number of bytes. So these are something you should actually absolutely become familiar with. You will soon love them. They're great. Okay, so I mentioned that we had a new problem coming up, and that's we've got the schema right. The next thing is we could have too many inserts. This is a very, very common problem in analytic databases because if you learn SQL the way I did, which was on relational databases, starting with Sybase, but I spent years working on MySQL, you're used to seeing inserts that look like this, which is, insert blah, 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 insert into some table values, blah, blah, blah. And you have them comma separated, and you might do a row or two at a time because you're typically doing things like, updating shopping carts or something like that. Small data. If you're doing this in ClickHouse, you're doing it wrong. So this is a very small insert. And the problem that you run into is that small inserts just beat the daylights out of your server because what's going to happen is ClickHouse wants to coalesce them into larger files. So this process is called merging. And what happens is that one of the virtues of ClickHouse is that when you do the insert of those values, they will create a new part. And this has a big advantage because it means that unlike some databases, the data that you insert is instantly queryable. It's in the format that, in the columnar format, and ClickHouse can quickly read it. The problem is that the files are so small that it's going to make the inserts much slower. So as a result, and we saw an example of that just a minute ago. So what ClickHouse is going to do in the background is it's going to run merges. So it will look for small parts, sort of groups of contiguous small parts, sort of in the order that they're inserted, and it's going to grab them and rewrite them to make bigger parts. And over time, it will end up with the largest parts that it can make up to a point, at which point it stops trying to merge them. So what this does is eventually, left to its own devices, ClickHouse will get to a part size that makes query efficient. But in the meantime, you have to pay for this in a couple different ways. One is it takes CPU time to grab these parts, read them in, uh, merge them, and of course you've got to sort them and do all that stuff, lay them out in memory, and then push them back out. The other thing is it's consuming I/O bandwidth. We call this write amplification. So what it means is when data is inserted, it's going to be rewritten again and again and again until the part becomes large enough that ClickHouse no longer touches it. This is a really important property of ClickHouse. It's similar to many other databases, but what it can do is it can swamp your system if this is happening too much, because it then takes up CPU and I/O bandwidth that's needed for other things like queries. So there's a couple of ways to get around this. In fact, there's many. I'm just going to talk about two. One is simply uh, batch the data yourself. This is a very simple example of how I'm inserting data. It's CSV data, and I'm just using ClickHouse as an HTTP interface that you can use to upload data. You basically just post it. This is an example of how to do that. So put the data in big CSV files. It could be in Parquet. It could be in, whatever format is convenient. Put it into, do it a million rows at a time. ClickHouse does not care how big these things are. Uh, you can pretty much use any size, and then you just push it up. Now, in some cases, though, that's not convenient to do, because imagine that the data is coming from something like FluentD, and using FluentBit, for example, for collecting, say, traces. And what you can do is set FluentBit up so that it can actually post the data out directly to ClickHouse. That's great. It's just that by default, FluentBit is only going to write 2 meg chunks. Those are little. So what we can do is use another trick, which is what we call async inserts. And the way that these work is that when you enable them, and I'll show you how to do it, you can have a bunch of clients simultaneously inserting to ClickHouse. And what ClickHouse will do is it will put those written rows into a single buffer, and then at some reasonable period of time, say after a half a second or after it hits a certain size, it's going to go ahead and flush the whole buffer out to storage, and you'll get one bigger part created from what were originally many small inserts. This is a great feature. When it was first introduced, it was kind of unstable, but this is a standard recommendation for how to deal with a small insert problem. And in fact, our KB has examples of the syntax. So I'm going to show you how to do it here. So there's just a number of kind of persnickety little properties or settings that you have to use. For example, enable async insert. You tell the clients to wait, blah blah blah. You can sort of read it off the slides, but the idea here is that I basically set up a user, and that user has what's called a settings profile that has the settings, so will automatically use async inserts. And if all your inserts just use this account, when they come in to insert data, they'll get merged automatically. So this is a really super feature. We highly recommend it. Um, so there's more that could be said about small inserts. You could, for example, use Kafka to buffer them up. You can read about that yourself. We do other webinars, and there's other documentation on this. What I'd like to get to, though, is a third area and opportunity, if you will, to make. Is it possible? Oh, here's a great one from Carol. Is it possible to enable async insert for Kafka-based ingestion? Well, there's two ways to insert into Kafka. Misha will probably comment more on this. One is to use the Kafka table engine, which Misha actually did a lot
Yep.
of work on. So actually, Misha, you want to take that one?
Yeah, sure. Yeah, so it's actually like for async inserts, uh, Kafka. If you use Kafka engine inside ClickHouse, actually it have the same functionality as like some same buffering functionality as a part of the engine itself. So we don't need to use async inserts, and actually they will not work if you'll try to enable that for Kafka. But Kafka itself really works like a very similar way. So it means that you don't need it for Kafka engine. But if you do the inserts from some external components from Kafka, so it means that you, for example, use, I don't know, Kafka Connect or some other Golang application or something like that, when in that case, you of course like then for ClickHouse it's usual insert, and you can do the async inserts also.
Great. Yeah, that's exactly the answer I would have given. It just sounds more authoritative coming from you, Misha, since you actually wrote the code. So, yeah, that's a great question. And in fact, putting Kafka in, there's kind of a balance here. A lot of people use Kafka because it does simplify the systems in one sense, like it takes care of the small insert problem. It splits it uses connections more efficiently because you don't have thousands of clients trying to, consuming TCP/IP connections. The flip side is you got to manage Kafka. So you can decide which one is better. Meanwhile, let's talk about bad queries. This is sort of like Anna Karenina. Um, the bad queries are, good queries are all the same, but bad queries are all different they're all, they're all different in their own way. So let me give you some examples and then we'll kind of generalize from that. So the basic thing is that when you have queries, that very small differences in what you ask for, like the specific data you want returned and how you ask for it, how you formulate your query and what language you use, can make huge differences in response. Here's a simple example where we have a query that's just asking for average, or that's asking for the average departure delay broken out by carrier. And that's a very simple query. And we could ask a more detailed form of it where we break the data out, not just by carrier, but we're going to break it out by flight date. So we're going to have more group by keys. And we're also going uh, to collect the tail numbers that are uh, associated with these delays. So tail number is the thing that identifies an aircraft. So we're asking for more information, and as you might expect, it it does cost you more. So, for example, this second query is 4.25 times slower, and the interesting thing is it uses vastly more memory, like over 20,000 times as much memory. The reason for that is that averages are very, very compact. They're when we're storing them in memory, we'll show you how that works. Uh, but they and as we split them out, uh, we begin to this unique exact actually stores a lot of information in memory. So one of the things you can do is you could say, well, do I really need to have all that data? So sometimes you don't. And so like a simple answer sometimes to things going slowly is just ask for less information, fewer group by keys, things like that. But there might be reasons why you have to have that information. It makes sense for what you're doing in your application. Let's dig into that. But first, what would be good to do is just understand what happens when we process a query. And basically, what happens is when we send that query out to ClickHouse, it's going to get parsed, turned into an AST that can be read, and we can make a plan. Deciding, okay, what's the sequence of operations to go fetch this stuff. Then we'll do a scan because this is just talking to one table. So it's going to be dominated by just reading the data out of that table. And we're going to collect the information from that scan. In this case, in the example server we have, it'll be four threads marching through. They're going to buffer the data that they're scanning in hash tables in memory. And then at the end, we're going to take all those hash tables, we're going to merge them together. We're going to do a sort so that we can get the data properly ordered, and then we're going to hand it back to the client. So this is the process that we're using. The key thing here is we have these hash tables, so we're going to be buffering this stuff in memory. And so what's useful to look at is the thing that really dominates the size of those hash tables is how much aggregation we're doing. That's a big consumer of data and memory. And what happens is as we're going along, uh, these threads will be scanning. They're maintaining these hash tables, and the key is going to the group by key is going to identify a um, a, a slot where it contains all the data that it is accumulating for that particular group by key. So the more this gives you some insight already. Like if you have a lot of group by keys, these hash tables are going to be pretty big. So these hash tables get larger and larger, and then at the end, what we do is the merge collapses them down, and then we uh, we then sort it and hand it back. What's interesting is the scan part that can be run in parallel. The merge can be partially parallelized. The sort can be partially parallelized, but the closer you get to handing it back to the user, the more likely it's going to be happening in on a single machine, for example, and in a form that's close to serialized. So what we want to do is knowing that these hash tables can get pretty big, we'll think about, okay, how could we make them smaller? And one of the simple ways to make some queries faster is to actually choose different aggregates. Here's a really interesting example of that. So picking up unique values over a period of time, like the unique visitors to a website in an hour or a particular website page. This was the number of tail numbers that were actually associated with flights on a particular date. If we use this aggregate called unique exact, it builds a hash table and it stores each individual value. So for every tail number that gets stored in there, the hash table gets a little bit bigger. We can change that and use another kind of aggregate that actually gives us an approximate count, but it uses a different data structure called hyperlog log, and that has a fixed size. And as a result, when we switch to this hyperlog log, it turns out we get almost exactly the same answer, but it's 15% faster, and more importantly, it uses 5 times less RAM. So this is a great example of making a very simple change in a query and getting much better results. Other things we could do, joins. So ClickHouse does, contrary to legend and reputation, ClickHouse does joins pretty well, but there's still places where you can actually get big performance advantages if you look closely at the joins. This is an example where we're uh, joining to get the airport name filled in as opposed to just like an IATA code, which is, just really short, like ORD or something like that. And in this original query, what we were doing was just joining directly. And in the second query, what we did was we broke out the query so that there's a scan, and that's in a subquery. This is a common trick to use, but it doesn't join on anything. What we do is go ahead and let that come back with our aggregation done, and then you have a much smaller data set that then gets joined against the airport name. And as a result, the query runs way faster and it uses less RAM. This is kind of interesting because Misha and I were talking about this before. ClickHouse does have an increasingly good query analyzer, but it doesn't make this optimization automatically. This is still one you have to do for yourself, at least in this particular case. What was happening? Well, what was basically happening was those hash tables that each of those threads that I showed you or discussed, they're maintaining each of them. They're kind of dragging along these airport names along with the additional information that they're collecting. And that's what's causing it to consume a lot of memory. It's also taking time to do that. So this is something again where knowing a little bit about how ClickHouse processes these internally gives you some insight into what you can do to fix it. And in fact, that's a very common theme with ClickHouse, that understanding what ClickHouse is doing inside is then really important to help you do the optimizations to make it run efficiently. So another question you may have is, how do we get these performance stats? Well, you can read them off the ClickHouse client, but you can get even more information out of system.querylog. This should be you should live in, if you're optimizing queries, this is a system table that you just want to live in. It provides great information. There are other tables that can help you, but this one is super, super useful. And it's all available through SQL. So actually, I think there is a, looks like there's one more thing on there was a, I think a page that accidentally got skipped. Uh, one more thing on query optimization, test it on real data. So we've been going bottom up and giving examples. So, but what you really want to do is put realistic data out there and run the queries against them. So, and then what you do is take the queries you don't like and you start to optimize them. So these tricks that I'm using, to optimize them, I would only apply them if the query was slow. Otherwise, I just leave it. I mean, if it's fast enough for your users and it doesn't take too much machine capacity, uh, you're good. You don't have to do anything special because ClickHouse gets a lot of stuff right all by itself. But in the cases where it doesn't, you then need to dig in and figure out why the query is going slow. Use these different optimizations that can make it much, much faster. It is very rare. You can't make a ClickHouse query faster, but it requires testing against real data. Problem number 4. So that was, we had bad choices on schema. We had too many inserts. We had bad queries. Another thing is just simply not having enough resources available to ClickHouse. So one of the things you can do at some point is we had that bad query, and let's say we couldn't fix it. Let's say that that was actually the best we could do after hours of optimization. Well, at that point, and this is the one where I made the bad partition choice, but let's say I couldn't fix that. Well, I may have no other choice but to throw hardware at it. So what can I do? Well, we were running on a 4 vCPU machine with uh, very slow EBS access, 125 megabytes per second. I can just upgrade it. So if I'm running Kubernetes, for example, it is very using for example, the the Altinity ClickHouse operator. It's very simple to just upgrade it to a nice big fat 32 vCPU uh, uh, server, and I can also change the I/O bandwidth to say 100 megabytes per second. Actually, I had the option to go to 2000, but right there, by making that change and then rerunning that query, I get much faster cold reads, and the hot reads are faster than the properly optimized schema. So that's an example where resources are really helpful, and you need to have enough of them. And sometimes when you have a problem, the right answer is just add more resources to buy some time while you figure out what the problem is. Um, but there's one thing that's really important to understand about resource management with ClickHouse, and that is that it's not just queries. ClickHouse servers actually do 4 things. They include, and so you can think of it as a menu. And every day, ClickHouse is doing queries, obviously, because you want to answer questions, but it's also inserting data. And we just talked about merges and how that can, processing the inserts themselves can be very expensive. For example, if you're parsing JSON or something like that, that can take time. You need to merge the data. That's computationally intensive, burns storage bandwidth. And then finally, updates. So the data that we load into ClickHouse is generally tends to be immutable, but not always. There's lots of cases where you actually have to go change data. You may need to remove tenants, for example, for GDPR. You may need to make changes because you get late arriving data, which affects measurements. So updates are in real systems tend to be pretty common. All of these things are happening at once in the same server. They all put pressure on CPU and RAM in the servers. They put pressure on your I/O, for example, your storage bandwidth. And this is a really important thing not to forget. If you're doing a lot of inserts or particular inserts, a lot of inserts or merges, you can put a lot of pressure on ClickHouse Keeper. So that's another place where you have to think about adding capacity uh, so that it doesn't become slow. Keeper is particularly important because if Keeper is answering slowly, your inserts go slow. And in fact, if it gets overloaded enough, your tables will go read only. This is bad. You don't want that to happen. So it's really important to, uh, when you're thinking about resource management, to do at least four things. One is when you're deploying a system, um, test on real workloads. And that is so important that it's like the number one thing that you want to do to solve this problem. One of the things that people ask is, wait, I'm going to deploy a system. I think it's going to be 100 servers. Does that mean I have to set up 100 servers? The answer is no. What you do is if you're planning, if you think you're going to need 100 servers, figure out what your total workload is going to be. So what are the number of rows that we're going to be loading into a single server, and just test on a single server and beat the daylights out of it. So this is a very common approach to capacity planning. Just take that one server and see what the capacity is of it. There's just one thing. There's not a lot of moving parts. You can optimize queries, get that to, sort of to the best performance you can, and then you can start adding replicas, adding shards, and building the full system. But the point is that it's use real data, the real data size, and make sure it's concurrent. There's a big difference between, because this is another thing that people don't see, is that the queries run fine when there's just one test user, but when there's like 400 analysts or sending the same query, it's a very different case, and that's where you run into problems. Second thing, detect trouble. So you want to have monitoring built in. These are obvious uh, things to monitor: CPU, I/O weight, RAM usage. You want to make sure that your buffer cache is not exhausted. You want to make sure that you're not hitting the network too hard. These are all things that we monitor, for example, in our cloud. Third thing, scale quickly when trouble hits. Ideally, you see it before it's happening. But if you do have problems with performance and they happen on Sunday, uh, our recommendation usually is, hey, just scale this thing up. So be able to scale. And again, Kubernetes is very helpful for this. You can just boost the VM size and then go home and deal with it on Monday. But you want to quickly apply capacity, because that then buys you time to go ahead and fix the apps. And that's the final thing. If you see resource problems, it's really critical to loop back, figure out what's wrong, uh, uh, you know, and fix it. And we have a keeper question, which is a great one. I know that Misha is giving
Yeah,
an answer for
yeah.
that.
I can type it or can answer.
Yeah, go ahead. Keeper is a good one. Yeah, if you want to just answer that one out
Yeah, so
loud.
it's actually how to monitor keeper pressure and state. Yeah, so to monitor the pressure, usually just like first of all, just let's check usual metrics. So not something keeper specific. So CPU, disk I/O, things like that. So one of the important metric for keeper is you need to ensure that the disk latency is really low, because it do fsync
Mhm.
and it really relies on those, and like round trip to the disk should be very small. And additionally, from keeper specific things, one of the most specific metric is outstanding requests. So it means that how many unprocessed requests are in the queue, let's say like that. And there are a few others, but I would say like the usual metrics plus outstanding requests. Sometimes you can also monitor also there is a metric showing the fsync time, so it really shows the round trip. So if you have no problems with those, usually it just works.
Yeah, and it's really important to keep keeper from getting overloaded, because what happens is not just that things get slow. If keeper gets overloaded and, for example, starts crashing, then your tables go read only and your inserts stop. And so keeper, and I bring this up because we know from experience it is tempting to under resource keeper, because when the systems are not loaded, keeper just isn't a very heavy user of resources. It's just that when it does, it's then difficult to get back out of it, because you then need to um, scale the systems up. You can run into problems when that's happening. That's a rare operation. So yeah, again, something to my personal feeling is just add, have good metrics, look at the things that Misha's talking about, add a bigger machine than you really think you need, and then forget about it. Let's talk about the last problem. And this is a really interesting one. And actually one of the most, the ones that we've over time had the most, really had the most, had to grapple with the most, and that is migration from non-compatible databases to ClickHouse. What do we mean by non-compatible? Well, let's talk about a compatible database. So Postgres, MySQL. This is a query that, selecting average departure delay. We've been playing around with that one for variations of that for most of this talk. You can run that query on MySQL. You can run that, should run on Postgres as well. Um, when you migrate the data over to ClickHouse, the same query runs. And you're the only difference typically is that it's going to run about, anywhere from 1,000 times faster to 2,000, whatever. You're just going to be amazed at how fast it runs. And the reason is that these are both tabular systems. Yes, Postgres and MySQL store data in rows, but they have the same data types. They use the same SQL dialect. They plan queries in kind of similar ways. And so you're working with a table. It's the same basic, logical or organization. These migrations tend to be fairly straightforward. It's just dump the data in, get it out of MySQL. It shouldn't have been there to begin with. It's things like, hey, uh, you know, uh, people accessing web pages, sort of things out of access logs shouldn't have been in there. Once you get to ClickHouse, things work great. Where it gets harder is you're migrating from other systems. A very popular one to migrate away from is Splunk. Another one is Elasticsearch. Um, these systems are challenging because they organize data very differently. What Splunk does is it has this very interesting format where incoming data like log messages from logs get turned into what are called events, and they aren't stored in a table the way ClickHouse does it with with parts, with columns, but in fact, the events are stored in what's called basically a full text index. So all the log messages will be the contents are stored in there, but they also have a big old full text index, which and if you're not familiar with full text indexes, unlike regular database indexes like a primary key index, instead of having the keys in the index, they have the values in the index. This is also called an inverted index, where it flips you can go look up the values. And what these do is they do two things. They allow you to ask questions where you scan over the data and you just ask, hey, give me all the records that have this random combination of keys. So for example, here's one where tail number uh, has a token, and what we're doing is breaking this up a little bit. So we're only taking the first four characters of the tail number, which is normally six. You can ask these questions very easily in a system like Splunk. Not only that, you can get the answer back really quickly. When you get to ClickHouse, this is a problem because ClickHouse is not organized in this way. Um, so there's a couple of so you need to rethink this because ClickHouse storing the data in a table, it has additional secondary indexes. We call them skip indexes. They're used to define, to find out where not to look to answer these questions. And when this is, when you're migrating from this system, you need to think about how to, if you want to achieve that same kind of performance that you got with Splunk, you're going to have to do some thinking to actually, uh, to actually achieve it. First of all, you're going to have indexes are per column, so you'll have to identify the columns where people are asking these questions. Then maybe you put a full text index in. Uh, Problem is that ClickHouse has full text indexes, but they've been rewritten a couple of times. The current version is in beta, so maybe and it's potentially very large. So that's something to think about. ClickHouse does have good Bloom filter indexes. Misha has done a really great blog article on them a couple years back, but they're kind of persnickety. They take some playing around with to get uh, uh, to tune them properly. But that's another option. And then finally, one of the things you can use in ClickHouse is the like operator. Like performs very, very quickly in ClickHouse. I think a lot of this is using, I think the underlying libraries on Intel use SIMD, if I recall correctly. So they are really quick, but that's another option. But for any of these options, you're going to need to, first of all, because people are coming from Splunk or Elasticsearch, they're used to doing searches like this. So you may be changing their lives if you don't let them do it. So you're going to have to do it. Second is you're going to need to test it on you're going to need to test it on real data to make sure that your choice of indexes and or queries solves this problem. This is where it gets hard. So the point we're really making here is that these are not when you're moving from a from a database that's not relational, you're moving to a different data organization. You have different expectations. You need to think about these as you move to ClickHouse. Many people have done this, have done this successfully, and we've helped many customers do this, but it doesn't happen by magic. And the big upfront thing is testing. So you want to test the queries under realistic load. If you have slow query patterns, I mean, one of the things you want to make sure is understand what the patterns are. That what is it the expectations people have based on these other systems? How can you replicate them in ClickHouse? And also be aware it takes time. The hardest thing to do in in database systems, is solve performance problems, because usually it's kind of house to house. You get one performance problem solved, and then you're just on to the next one, which is right behind it. It may take you a while to solve all the things that are blocking performance. So this is something that's really important to understand how to do. And it applies not just to Splunk, not just to Elasticsearch, it even applies to databases like Snowflake, where there's a lot of automated optimization of the partitioning, the, uh, the codecs, the compression, the sort orders. That stuff is done for you. You don't see it. When you come to ClickHouse, you need to make those choices yourself. So you need to build in time, and you need to think about testing. By the way, speaking of testing this sort of thing, I love the system log messages. If we're using indexes, this is an example where I can see that my Bloom filter index is wiping out, is telling me not to go look at least half uh, of my granules. So it is help. This is not very good. I expect it to wipe out a lot more of them, but this is information that you can use to help guide you. Um, so that's it. We've hit the end. We can stick around to answer a couple more questions, but these performance problems are very, very common when people come into ClickHouse or when their systems grow. So things you can do to avoid them. Bad schema. Well, tune your schema to reduce IO. It's and again, um, make sure this is yet another place where you have put realistic amounts of data. You will quickly see what's happening. ClickHouse has very powerful tools to help you optimize the schema in the form of the system tables. You always want to make inserts as big as possible, but not bigger. You do need, if you need data in 30 seconds, you can't wait 30 seconds to put it in. You need to put it in, say, in 5 seconds, and then because that gives the rest of your pipeline time to move the data. But use some reasonable value that is consistent with the SLAs you're meeting. Queries, test on real data and fix the slow ones. And this is where we keep saying realistic, put real workload on it. Use a single host. If you're building a large system, just use a single host, but beat that host up. Same for hardware. Test the hardware on realistic workloads, particularly concurrency, particular data size, and be able to increase it before you hit problems. And that means not just having the ability to scale it up to a larger instance size if you're running in the cloud, but also have metrics that tell you, hey, we're running into trouble before you actually start to see things fail. And then finally, if you're migrating from a non-relational database, plan time into the schedule. Think about testing. Think about what it is that why is it that people like Splunk? There is a reason why people pay absurd amounts of money for Splunk, because it's a pretty good database and they charge for it correspondingly. So when you come to a new database like ClickHouse, you'll want to make sure that you're taking into consideration the good things that those databases do. You don't just drop it into ClickHouse and start saving money. You actually have to do there's a trade-off between the different ways that databases organize things, and you need to adapt to that to get the full value for that from that investment. And so finally, don't assume ClickHouse will be fast. It is in good hands, and when it's been properly tested and properly tuned, It's really great. It's the best and fastest database I've ever worked with, but you need to test it and prove it for yourself and make the changes and the investment to get the speed. And that's it. So if you have questions, we'll take them now. I think we've got a big one here that, oh, great. Oh, yeah, we're going to stick around and answer a few questions here. We've got, Misha, I hope you have a couple
Yeah.
minutes. Um, so yeah, one thing, I sent a bunch of connection requests out on LinkedIn. Thank you so much for folks who answered. I'm sorry I got them out a little late this time around. But we also have a guide to TTL. Somebody asked in LinkedIn about it. If I'll hold this up, uh, the QR code on the left will get you our TTL guide. You can contact me on LinkedIn if you want to connect, and we're hiring. If you think you could do this better than we could, we want to talk to you. So let's see. All right. So let's go.
Yeah, probably
Yeah,
I
yeah,
can
go for it.
pick I can pick some of those. Like I would start maybe from the one with joins and group buys, and the
Yeah,
question is about like new features. Like right now there is a option to spill the join data and like those hash tables data on disk, and the question is about like should we still prefer to use the old uh, recommendations like we
yeah.
to fit the right hand table into RAM? Well, the answer actually is yes. Yeah. So if you can do that, it's like every kind of spilling on a disk, every kind of swapping is always worse in performance. So it's not something that you do just to make it fancier. You do it because you have no other choice. So if you're not fitting into RAM, you need to use swap. If your join is not fitting into the RAM, you can use that spill on disk. But if you can fit into RAM and if you can run the thing all the things like old school way when you have like the right hand table is in RAM, that's better. So it means that you can just make it faster. And if you enable that spilling on the disk, you make the joins slower, but they will eventually finish and they will not die because of out of RAM. So if you have choice, just just try to make of course try to make everything in RAM. And if it's not a choice, not possible, then just go with Spring.
You know, Misha, one
Hmm.
thing we didn't talk about in this, that wasn't in the slides, was dictionaries. I I think those were developed really early on in ClickHouse, and they're still really powerful um, mechanism
Ye- mhm.
because they allow sharing of that right, like sort of the right hand side of the join across a bunch of
So
different
just like having
processes.
it ready all the time in the
Yeah,
server memory, like that's a cool feature. So like in many cases, like for like slowly changing dimensions for star schema with some extra dimensions. I don't know, like resolving client ID to client name. Like for those type of things, dictionaries are the best possible thing you can do. Like it can be much better than the joins. But
yeah.
of course, if you just use the traditional joins, if you use some tool which writes the joins for you, like the joins should also work. But just remember that you can like there are more options in ClickHouse. Mm. And uh, like this one, let's mark it done. About the materialized views for one row table. Oops, probably I just marked the other one as but I'll get back to that. Sorry. Um, so materialized use one row table and 10 or 20 silver tables. Um, well, having materialized use, like many materialized use, triggered by a single um, by a single table usually is not the greatest practice. Why? Because every single insert into that original table will trigger the sequence of inserts to 20 tables. So it's like kind of after insert trigger. So every time you insert to the main table, like it will trigger 20 more inserts. And obviously that will impact insert performance a lot. So it means that every single insert become not a single insert anymore, but 20 inserts. And like you'll need to ClickHouse will need to deal with mergers inside 20 tables, not inside one table, and so on and so far. So it's actually like it's exploding the like it's just generally it's fun out of the writes. Usually it's not a good practice. If you can avoid that, please avoid it. The like uh, typical way of avoiding that is either pushing something inside the main table itself, so creating projection generally, or if you need to have some that several tiers of of the data like bronze, silver, and gold, you can just make the movements between those tiers not in real time, just not trigger them by every single insert, but trigger it, for example, every 10 seconds or every 1 minute or something like that. And just like this way, you will not impact like the costs of filling the silver layer will not will not impact the insert speed. So your insert will be still fast. You can still fill your bronze layer very quickly, but every 10 seconds or every 1 minute you trigger a flash from the freshMOS data from bronze to silver tier.
We've got the question from Carol about the sharding, which
Yeah,
it's in.
yeah, I
We'll take that one
accidentally,
and then probably
yeah,
close
yeah.
up.
Yeah, I accidentally clicked that wrong one, but it's for sure sharding is a very important topic. It's quite a broad topic. Probably it will not be able to answer that in 1 minute, but for sure it make a lot of difference how you shard data. So one of the main decision points here, if you have several tables, like you have some normalization, if you can do so sharding can help you to make the joins locally. And that's very important because if you can't do joins locally, then the joins will go through generally the nodes will need to exchange a lot of significant amount of data. That's not something that we like. And of course, it can also impact the speed of the queries itself. So if you need to transfer a lot of data between the nodes, it always the network speed is not something that you can easily scale. So of course, there are some good network cards, but you can't, like, they will never come very close to the speed of the RAM, for example. Yeah, so like it's quite right, relatively slow place. And if nodes need to exchange a significant amount of data, you will be not, so the query will not be scalable linearly. So it will just spend a lot of time on data exchange. And the amount of a data exchange is heavily impacted by the sharding schema used.
Yeah, one thing that we've run into as well is that because when you have shards, you're going to use a distributed table to query across them. You need to be very careful about what happens that and that node where the query hits is called the initiator. There are cases where if you're not careful, if you write very complex queries, it will force a bunch of processing onto the initiator node, and that will become a huge bottleneck. I've seen cases where the actual scans on the shards, took, in aggregate, took a few seconds divided across, like dozens of threads, but then we would take like 100 seconds to process the data on the distributed, uh, you know, in this distributed table engine, because there's some things that end up getting serialized. These are cases where this can happen. Like if you write complex queries with a lot of CTEs in them, you can sometimes really get tied in knots trying to process these across shards. So keep it simple. That's usually the way to solve that problem. And yeah, I think there was one thing, adding shards in real time. Actually, a key thing with that is if you partition by time, you can add shards very simply just by adding more hardware and let the new data redistribute. If you don't have a particular, like if tenants don't have affinity to particular shards, this is another thing we need to think hard about the sharding key. But the in the best case, you just add more hardware and then let the shards fill up. And if you're keeping data for 14 days, for example, after 14 days, your new shards are all equally balanced with the old ones. So I think that we'll call it a day. Misha, thank you so much. You helped us go from a, a subpar talk to definitely above average. I hope you've all enjoyed this talk. It's been wonderful giving it. Thank you so much for the opportunity to present. If you have more questions, we're reachable at altinity.com. You can come to our Slack channel. You can contact me on LinkedIn. We basically we love databases and we love to help. So yeah, give us a call and good luck with your ClickHouse applications. And thank you very much for joining us today.
And thank you guys. See you.
Thank you, Misha. Bye bye.